Bob Swanson here, ICC Astronomy Instructor, and this is a video that hopefully will help you with the Module 5 lab activity. This lab activity involves hydrogen energy levels, and essentially it deals with the nature of light. And it's a rather abstract concept, but a very, very important topic because without light, there's really no astronomy. Astronomy really depends upon those little pinpricks of light we see in the nighttime sky. And that's the only information we get about those stars that are millions, sometimes light years away. And so light is a really, really important topic. The problem is we see light, but we don't see the waves that make up light. We don't see the particles that make up light. So some of this may seem rather abstract, but it is very, very important. So hopefully you found your way to the Module 5 lab activity page, and I do encourage you to go through the background material. When you click on this link, it's going to take you to the hydrogen energy levels activity. Go through the main content, go through the energy levels, the light, the transitions, before you jump into the simulator. The first page on the student guide does involve some of this background material. So I'll walk through it really quick, but I'm not going to read it all to you. The one thing that is very vital, and in fact the first page of your student guide deals with, and here's what the student guide looks like, it talks about this Bohr model of the atom and the quantum model of the atom. You know, everything is made up of atoms. We can't see atoms. They're so small we can't see them, but we can have models of what they must look like, and we know these models have the characteristics they do because of the way that matter behaves. So this first page in the background describes two different types of models, the one being what's called the Bohr model of the atom, which it has similarities to what's called the quantum model of the atom. They both have a positively charged proton at the center of the atom. That's where most of the mass of the entire atom is concentrated. And then you have a negatively charged electron outside the nucleus. Now in the Bohr model of the atom, it was almost pictured as being a little planet orbiting the proton, being somewhat like the sun. It turns out that's not the way atoms behave. But it's a useful model anyway, because what Bohr proposed was that the electron can be in certain positions away from the proton. It can't be anywhere. It has to be at certain specific locations. The quantum model of the atom latched onto that idea, but also latched onto the idea that the electron is not just like a little planet. Sometimes it acts like a particle, sometimes it acts like a wave. It's not it never can be pinpointed as to where it's going to be. You can only have probabilities of where the electron might be. But that idea that the electron takes on certain energies that are discrete. It's not a continuous energy. It's certain energy values. That is also a characteristic of the quantum model. So those energy levels are what are called orbitals. And so this whole thing describes these energy levels that an electron can exist at. So that takes you on through this page. Now, of course, an electron can either move up or down in energy levels depending upon whether it absorbs energy or takes or gives off energy in the form of light. Now when we talk about light in astronomy, it's not just visible light that you and I see. Here's a little chart that shows the full spectrum of light. This little sliver is what we see. So if you think the human eye is wonderful, it's not. The human eye is pretty lousy. The reason being, we miss out on a whole lot. We miss out on all this that's happening down here. We miss out on all this that's happening up here. So the human eye can only see a very, very small sliver of what overall is what we call light. Any electromagnetic wave is light. We only see the small sliver, those visible wavelengths, Roy G. Biv, red, orange, yellow, green, blue, violet. But we miss out on ultraviolet, gamma rays, infrared waves, microwaves, radio waves. These are all types of light. We just can't see them. However, we can build equipment that can sense these things. That's why astronomers do use radio telescopes. They use gamma ray telescopes and X-ray telescopes because sometimes it's useful to be able to see in those wavelengths in order to learn more about the universe. But anyway, that's the background on the electromagnetic spectrum. One thing you will notice is that no matter what type of light you're talking about, all light travels at what is called c, the speed of light. It's a huge, huge number. You can look it up. 3 times 10 to the 8th meters per second. That's 186,000 miles per second. So light travels very fast. But it doesn't matter whether it's radio waves, X-rays, visible light, infrared. it all travels at the same speed. In order for the left side of this equation to be the same, and yet these all have different wavelengths, that means that the frequencies must be different. And it turns out that yes, as you go, and this is the way that you read this chart, the frequency increases as you go from left to right across this chart. So radio waves have lower frequencies than visible light, and visible light has lower frequencies than gamma rays. Inversely, because the C must be the same, if a certain type of wave has a greater frequency, it must have a smaller wavelength. And so if you look at this bottom line, this shows, I'm sorry, right here, this line right here, the wavelengths, they're increasing from right to left. So therefore a gamma ray has a shorter wavelength than a radio wave does. That's how you read this chart. And it turns out that even though the C is a constant, the speed of light is a constant, because the wavelength is inversely related to the frequency. One thing that's important to understand here is that the energy of these different types of light is not the same. The energy is proportional to the frequency. So a light variety that has a greater frequency is going to have more energy. That's why we don't worry so much about radio waves. That's why when we have cell phones, we use microwaves for cell phones. You put it next to your head, it's not a big deal because that's not very energetic type of light. However, we limit our exposure to X-rays. We limit our exposure to ultraviolet rays and gamma rays because these all have higher frequencies, and therefore that is more energetic type of light, and it can do more damage to your cells. That's when we start worrying about overexposure and the potential for cancers and that sort of thing. So these two background will help you in the first 2 pages of your student guide. Like I said, electrons can change orbitals. They can change energy levels. And so this whole page is all about that. When an electron absorbs energy, it will jump up from a lower energy level to a higher energy level. The ground state is the most basic level, and then as an electron absorbs energy, it can be excited. It doesn't stay excited very long, as you're going to see in the simulation, but it can be excited into a higher energy level if it absorbs the right amount of energy. It's like a ladder. You can't stand between rungs. You have to be standing on certain rungs, and if you gain some energy, you move up to the next rung. If you gain the right amount of energy, you move up to the next rung. You can't just absorb any kind of energy. It's got to be the right amount of energy in order to allow you to change energy levels. And I think that's where I'm going to stop this video. I'm going to pick up on the simulation now in a second video. So I've blabbered long enough about the background materials.